Good afternoon to one and all. Is it audible? Anybody can unmute your mic and say, is it audible?
Yes, sir.
Okay, thank you. Is presentation visible?
Yes, sir.
Okay, thank you, ma'am. So, a very good afternoon to one and all. Welcome back after a long duration. You were attending placement classes, and one day went off in an holiday. So, we'll start today's session. The session on global positioning systems, unit number 1. Okay. Yeah. In today's outline or in today's presentation, we are going to see about a differential global positioning system, static and kinematic positioning, datum transformations in the form of 2D and 3D, and dilution of precision, which we call it as a DOP factor. So these are the 4 different topics that we are going to see in today's session. So the basic concept of differential GPS comes by the point positioning accuracy of the selective availability system. So the basic concepts lies in that. Okay. So the degradation of the point positioning system's accuracy, which was given by selective availability, has led to the development of this differential GPS. So this is what I said, that we need to be aware of selective availability. So the degradation in the point positioning, which had led to more errors, the accurate positioning of the system was unable to be identified used by the SA system. So this has led to the development of an differential GPS, which is basically based on 2 or more receivers, where one receiver will be your stationary, or we call it as an reference, and another will be in motion. Okay, so that's what the technique is based on: use of 2 or more receivers, where one would be your reference or a base receiver located at a known point, and the position of the remote receiver, which is to be determined. So this is a basic concept. So for this achieving of this differential GPS, what is required is that we require at least 4 common satellites which tracks simultaneously of some objects or some celestial bodies or some satellites. So at least 4 common satellites are being required. So that tracks simultaneously at both the sides. So the known position of the reference is calculated. Since we know the position of the known system, the known position of the reference receiver is used to calculate the corrections of the GPS. So with respect to the moving object, we can calculate where the actual positioning of the system is. In order to know the position of the unknown receiver, we need to correlate it with the known receiver's positioning. So they were correct. These corrections or error rectifications are being done through the telemetry of the roving receiver, which allows the computation of rover position, with far more than the single point positioning mode. So this rover is your point where the this one, this is your point. So this is your rover point where another receiver is in motion. So this rover's position is to be determined. So this base represents your known position of the receiver. So this is your satellite which monitors. So like this, four will be there, minimum four, and the correction can be done accordingly. So then, an alternative to the navigation mode was the surveillance mode, where remote receivers broadcasted the raw observation data to the monitor station, where the exact position of the rover is being computed. So this surveillance mode had an advantage that the roving receiver does not have to perform a large number of computations. Large number of computations can be avoided by using this surveillance mode in differential GPS. And how to correct them, or how to rectify the errors is by two methods. One is a reference receiver at a known location calculates the position using the same set of satellites. It uses the same set of satellites as in the roving receiver. So the difference of the known from the calculated position gives position corrections. So how much difference we get from the rover with the base is being computed, and these are being applied to the improving positioning. So that will be added. And the advantages is that this system is simple in design, but it requires more complex satellite selection. So which satellite gives us the exact set of positioning? Determining that or choosing that satellite is a complex thing. Okay, because the satellite will be in motion with respect to Earth, revolving around Earth. So choice of the satellite is a major disadvantage. So second method is that for correction, the pseudo range corrections are derived from the difference between the calculated ranges and observed pseudo ranges at the reference sites. We'll be having a reference site. From that, we'll be calculating different pseudo ranges. So difference of them will give us the corrected technique to be applied. So the observed pseudo ranges minus the corrected. So these have advantages of having more flexibility, higher accuracy, accurate positioning of the systems can be located, and the disadvantage is that it is more computing, more computational effect is required. Algorithms are more difficult to compute. So next is your high accuracy. How do we achieve this high accuracy? In terms of some examples, so GPS users are very different, that they vary between a few hundred meters and centimeter levels. So the CA course or acquisition code ranges with accuracies of 1 to 5 meter level is acceptable, and accuracy level real time up to 20 kilometer is acceptable, and ambiguities on the fly board using dual frequency receivers for a higher accuracy is acceptable. So we can have this many in these ranges. So next is your wide area DGPS, wide area differential global positioning system. So this uses a network of GPS reference stations that covers a larger territory reasonably accommodated by a single reference station. We can use a single reference station and gathering information for a larger territory or larger area. So the advantages of this W is first one, more accuracy. Second one, larger coverage. We can cover large bodies of water, river with a single reference. Only one reference station is enough such that we can accurately measure whatever surveillance or navigation that we require. Next advantage is that This network can have a single master station collecting range corrections and processing them and giving it to the monitor stations. Master station is different from monitor station. So master station will do controlling, and it will collect the ranges from monitor stations, process them, and send it back to the monitor stations again. Using in this wide area DGPS, and this may have additional delay due to communication error, so that can be rectified. The communication error in the or communication delay in the DGPS are being overcome by wide area DGPS. And these wide area DGPS corrections are generated by using two main systems. One is measurement domain approach, and second one state space approach. I will highlight it. Measurement domain approach and state space approach. So in measurement domain technique or the approach, the differential corrections of the individual monitor stations are weighted to form one set of corrections. So what are the difference between the reference and the actual positioning is being calculated, and they are weighted to form a single set of corrections, which we called as measurement domain approach. So this is a simple concept, but there are some disadvantage also. So which is accuracy depends upon the distance of the user from the nearest monitor station. So if the accuracy of the point which is to be determined is very near to the monitor station, easily we can accurately find it. If it is far away, it is difficult to find in measurement domain based approach. So whereas in the state space approach, where orbits, tropospheric or ionospheric systems can be modeled, the errors are very much. So for this, the state space approach is advisable. Okay. And the errors from which we get are correlated to each other with a reference station. So thus the accuracy is consistent over the entire network. So this is how we do it in state space. Determining orbital, tropospheric and ionospheric errors and evaluating in a specific network solution. Next is the virtual reference station. Virtual reference station. So in this I can show you a virtual reference station. We have a base X, baseline X, a rover X here, which is in motion. So this is your satellite which is monitoring all the activities or whatever the information that we require, which is being given by the satellite. So this satellite will have a duplicate of that in virtually at your base in the Earth's surface. So that we call it as virtual. Virtual. So this is what virtual reference station. This virtual reference station came as a boost to the WADGPS, wide area differential global positioning system. Since there were different locations, distant monitoring stations, so they developed the correct ranges for this, and even the observables of non-existent reference station at a user-specific position was determined. So this is mainly for real-time kinematic applications, RTK applications, which require a shorter distance for reference stations to have good ambiguity. Next, coming on to the data link. The data link is an essential part of your GPS, which connects the two devices, as we have a data link layer in our network theory, so in our communication networks. So this link is always a type of radio channel. So the radio channel will have two parts, hardware and software, which are compatible with the monitor station and remote stations. So these have code ranges that requires data transfer of 200 bits per second and data rates of at least 2400 bits per second to 19,200 bits per second depending upon the update rate data rate. If it is a real time, if it is static, we require only 200 bits. If it is real time, we require 2400 bits per second to 19,200 bits per second for updation. So these are mainly ground-based and space-based communications that are capable of transmitting DGPS corrections. So where do we place these satellites? Is that or where do we apply this DGPS? Is that it is being found in Inmarsat, International Maritime Satellite System, Geo satellites, LEO satellites, geostationary satellite, and low Earth orbiting satellites. All this provides DGPS throughout the world. And this WAD GPS is relying on the satellite communication for transmission of differential data. It is used in remote mountainous regions that avoids difficulties in receiving ground-based radio transmissions. All works on radio link for communicating. So how do we find the range of that is what we are going to calculate. Okay, so the range varies with an factor called radio broadcast radio data system, which is being used in our existing FMs radio data system. So the establishment of the terrestrial is much cheaper than the satellite system. So the data will be always transmitted through a conventional data radios or radio cell phones or mobile phones or cellular phones in the form of RDS, radio data system in DGPS. So an improved technique in the data radio channel or DARC, which was developed in Japan, supported a higher data rate than RDS. So an possibility of pseudo lights, which we call it as pseudo and satellite, that refers to a transmitter that emits radio signals like a GPS satellite was being developed, having higher data rate than radio data systems. So this used radiation power in the frequency of radio link in VHF band, UHF band, very high frequency range band and ultra high frequency range band for terrestrial. All these things which we are seeing is for terrestrial. So how do we find the distance between the maximum ranges? Is that D is equal to a factor 3.57 square root of K. So this K depends upon the vertical gradient of refractivity and it should vary only from 1.2 to 1.6. The choice of this is depending upon all the terrestrial conditions. So in some terrestrial conditions we may choose 1.2. If it is hilly region, if it is surface, we consider it as 1.6. In that range we can have. And D is equal to 3.57 square root of K of square root of HT plus square root of HR. HT is the height of your transmitter antenna and HR is the height of your receiver antenna measured in kms, kilometers. And the satellite communication will allow a maximum frequency in terms of gigahertz, which is 19200 bits per second over longer distances. So this is your RTCM format having 64 message types. RTCM is your Radio Technical Commission for Maritime Services. It is a special committee which is using all these frequency bands. Very low frequency radio data systems, RDS, ultra high frequency, UHF, cell phones and Inmarsat. So the equivalent band baud rate required for them. And as we see, the format for the messages is identical to that of your GPS navigation system, having a sequence of 30 bit words. You have 30 bit words. I'll show you those 30 bit words here. So each message starts with a header, as you all are very familiar with communication networks. First word, a fixed preamble, then a message type identification and a reference station identifier. Second word, frame time tag in the form of a Z count, sequence number, message length, and a reference station, a health indicator. So this health indicator indicates the status of the satellite, whether it how much power supply is left out, how much days this solar panel can work, how much more energy is present, how many days it may take more to work, or how many years is the lifespan of this thing. All those things will be in your health indicator. And in some messages, we will be having a third word with your header, and always we have will be having last six words, 6 bits in each of the word as parity bits. And you all are familiar what are the parity bits, which is used to check error and detect errors, parity bits. So this is your message format, message type of RTCM, which is version 2.2. So type 1, if it is being labeled as 1, it is GPS differential correction. 3, GPS reference station parameters. In the 6, null frame filler. We don't have. 9, partial set of type 1 messages. 16, special GPS message. 18, raw carrier case measurements. 19, raw code range measurements. 20, carrier phase corrections. 21, code range corrections. All the information will be present in them. So this is still your DGPS. Okay, till we have, if it is still 30, and still we can implement till 36. If we have 31, it is GLONASS differential correction. 32, GLONASS reference station parameters. 34, partial set of type 31 messages, and 36, special GLONASS message. If we include GLONASS in this, we can use this. So coming to the next topic, static and kinematic positioning. So we all are familiar with positioning. In that, two types are there, static and kinematic. So that we are going to see. Static surveying is the most commonly used method, where only the basic thing is that there is not much more abstraction in between the measurement and the object of the what do you call it, base station and the object which we want to determine. It is not much abstraction except the sky. So these conventional static surveys require observation periods depending upon the baseline length, number of visible satellites, the geometric configuration, latitude, longitude, and altitude, and the method being used. So this accuracy will get with a baseline length of about 1 to 0.1 parts per million, and it can be extended for up to 100 kilometers. 100 kilometers, that's all. So we have a conventional receiver L1. We have two receivers L1, L2. So if you use only one L1 band, so the conventional static is 30 minutes plus 3 minutes per kilometer to await. And if it is rapid, 20 minutes plus 2 minutes per kilometer. If you're going for L1 and L2 bands, conventional static is 20 minutes plus 2 minutes per kilometer. Whereas if you want to find rapid static, 10 minutes plus 1 minute per kilometer. So this is your rover, this direction which is being given. Here X is this is your rover, this is your satellite, this is your reference baseline. So what is this static positioning is? So this static position includes the rapid static technique based on fast ambiguity resolution techniques, which use code and carrier phase combinations on both L1 and L2 frequencies. So which are giving optimum satellite geometric that is restricted to about 20 kilometers baseline. So up to 20 kilometers baseline we can achieve on dual frequencies, dual frequency receivers. So this is based on the principle of having at least 4 satellites having having good geometry and normal atmospheric conditions. If the sky is clear, no rain, no fog, no thunderstorm, and all, this satellite positioning will work better. Only 4 is enough. And the uses of static survey is state, country. Okay, here it should come it as country. It's not county, country. Typing mistake. State, we can survey state, we can survey country, or even a local control surveys. We can use it for photo control surveys, boundary surveys, deforming surveys. Next comes your kinematic relative positioning. So this kinematic relative positioning is that the rover will be in motion with respect to your reference stations. So these kinematic surveys are most productive, which gives more accuracy of the exact position within no time. So this is being characterized by stop and go technique, by alternative stopping, moving one receiver to determine the position of fixed points along the system. So this increases in accuracy where we have so many measurements to be done. If we have so many measurements to be done for a single receiver, we can use this kinematic positioning method. So the resolution of the phase ambiguities starts before the survey. The required lock-on has at least 4 satellites throughout the entire survey. Means that the kinematic surveys are considerable not only in occupied satellites but also in routing. So routing in the sense movement of the receivers. So whereas in static we can accurately position only the non-movement of your objects or non-movement of your tracking systems. Whereas this can be used for your traveling also. So if an object is in traveling, we can easily identify its positioning. So the drawback is that after the initialization of the survey, a continuous lock on the 4 satellites cannot be maintained. So that is a drawback. We cannot rely on only those 4 satellites. So that is a major drawback in this. Users or applications is used in suburban subdivisions where there are no much of the hangings on the road or no larger trees. So there you can use kinematic positioning or kinematic technique of positioning. So this will determine the position of the receiver mounted on all terrain vehicles that may travel. So traveling on terrain vehicles can be easily done. And the three-dimensional coordinates of the vehicle mounted on receiver gives high accuracy of positioning on the topographic map. So in short, we can say that this kinematic method is suited only for wide open area having lesser obstructions. If their obstructions are very much lesser, you'll get more accuracies. And in addition to the static and kinematic, we have a third one called pseudo kinematic relative. So pseudo kinetic relative is that it is an intermediate between static and kinematic, which involves having occupying a pair of points for 5 minutes. The thing is that when you want to use pseudokinetic method, this method will use that for 5 minutes or for some duration, the system will not acquire the positioning. So for 5 minutes, it will acquire the position, whatever it is. So then after 5 minutes, it will move to the next point. After 5 minutes, it will go to the next point. After 5 minutes, it will go to the next point. So there will be a halt in duration. So which is we call it as pseudokinematic positioning. So for after every 5 minutes, it will halt and it will compute the data. That's what when we use Google Maps, it will show that some desired points. This was updated 10 minutes back. This was updated 5 minutes back. This was updated 1 hour back, and all. 1 hour back, this was the position of this object in real time tracking. So the best use of this pseudokinematic is that when points are to be occupied or to be determined along the roadside, the observer can quickly move between the setups. There is higher accuracy achievable if the integer bias. This is not only for 5 minutes, you can extend it also. It depends upon the type of application that we use. If you want it to measure for 10 minutes, you can do it. 15 minutes, you can do it, and it goes on. So it depends upon the observation time. Okay. So the disadvantages is that restriction of the method to the local applications, rapid positioning of the system changes, and weakness in the necessity of revisiting the site. So these are the disadvantages. Whereas applications, we can go for photo control surveys, lower order control surveys, and mining surveys in mines. So how do we see all these three different surveys? Is that practically you can have an mixture of all the three methods depending upon the application on a single frequency. We can use any of this three methods in a single device. If that is used, it will be more effective. If you want to determine static positioning, we can easily find static. If you want kinematic, we can easily determine kinematic movement of the objects in live. If you want to do pseudo kinematic, also can be done easily. So the static and pseudo kinematic methods are used to establish a broad frame of control and to set points on either side of the obstructions. This lays as a bridge between them. Whereas kinematic surveys are employed to determine the coordinates of the major portion of points using static points as control and checkpoints. So, although there is much more research is going on all these mixed surveys, the cost plays a major role. So, if you use a dual frequency, the reduction in the cost will eventually obviate the use of methods, which can be neglected. So, the instruments used gives us a satisfaction that sub-centimeter accuracy and sophisticated software will eliminate loss of lock problem. So locking problem can be avoided in kinematic surveys. So coming to the next topic, datum transformations. Datum transformations are used to relate the global positioning with some of the coordinate systems. So as we had seen in your electromagnetic fields, we have three coordinates: rectangular, spherical, and cylindrical. So those three axes are being considered here. How do we correlate that? Okay. So a geodetic or a datum defines relation between the global and these three local dimensional coordinate system in the form of rectangle. We take it as rectangle. One is latitude, another one longitude, another one altitude. So the primary task when combining the GPS and the terrestrial is that the geocentric systems of WGS 84 coordinates to the local terrestrial coordinates. The local episoid is linked to the non-geocentric Cartesian coordinate where the origin coincides with the center of ellipsoid. The plane coordinates with the Gauss-Kruger coordinates are obtained by mapping the local episoid into the plane with the concept of data transformations, and the GPS fiducial point gives us much more information about the orbit moment in the past, so which can be kept as a reference point and which can be used for further examination. So these are the points where the measurement of accuracy can be playing a vital role in VLBA or SLR. So the concept of fiducial points is quite simple. Having a GPS campaign, we require at least three fiducial points. So that's what the fiducial points are: latitude, longitude, and altitude, the area of campaign, and are also equipped with receivers. So this enables the transformation of GPS coordinates into frame of fiducial points by a three-dimensional similarity confirmation. So this is your diagram for that. The three-dimensional transformation is that with respect to our rectangular coordinates, x-axis, y-axis, and z-axis. So we're going to use your Helmet transformation between the two sets given by xt, which is equal to c plus mu r into x. So c is your translation or the shift vector, mu is your scaling factor, r is a rotational matrix. So the components which are being used for your shifting is given in 3. So we take C1, C2, C3. So the representation in successive rotations is being given by the orthogonal matrix R is equal to R3, alpha 3, R2, alpha 2, R1, alpha 1. So expand it. On expansion, you get cos relation between 1 and 2, relation between 1 and 3, relation between 1 and 2, 1 and 1, 2 and 1, 2 and 2, 2 and 3, relation between 3 and 1, 3 and 2, 3 and 3. So these three-dimensional representations are unknown parameters and they can be identified by common ideal points. So this means that at the same point and in both the systems we can identify xt and x, which will give us three equations. So there are two common points which will give us additional information to solve the unknown parameters. So there will be a redundant common point information that is used and to determine the system's positioning by using least square method. Least square method for determining the unknown positioning. Since the parameters are mixed, non-linear, so we need to linearize them. So by approximating the values of mu naught, r naught, and c naught. So in datum transformation in WGS and the local system, mu naught is always considered as 1, and the relation will be mu is equal to mu naught plus del mu, which is 1 plus del mu, since mu naught is 1. So substitute, we'll get all this as 1, and del alpha I as 1, and sin del alpha I is equal to del alpha I. So choose only the first order terms and substitute here. So we'll get R matrix as this, which is I plus del R. I is a unit matrix, del R is a skew symmetric matrix of differential rotational type, and this can be approximated. R naught is equal to I. So finally, shift vector can be split up into C is equal to C naught plus del C. So where the approximate shift vector can be given as C naught is equal to xt minus x. So thus we will get xt minus x is minus C naught is equal to ai into del p. So this is a matrix representation of three-dimensional unit vectors, identity matrix, and the equal relation for rho. So what happens in this three-dimensional transformation is that this transforms the plane coordinates of the common points into ellipsoid surface points by using appropriate mapping formulas. They transform the ellipsoidal coordinates of the common points into Cartesian. Then they determine the 7 parameters of Helmut transformation using the coordinates and the common points. Then for network points other than the common points, they transform the coordinates using transformation parameters. Then they transform the Cartesian coordinates computed into ellipsoid coordinates by iterative procedure, doing it again and again. And they map the ellipsoidal surface coordinates computed in previous step into plane coordinates for mapping the appropriate formulas. So this is what a 3D does. With this, we can accurately position or we can accurately determine what is the point of existence of that system is. Okay. So advantages. There is no prior information required for the 7 parameters, and disadvantage is that the ellipsoidal heights or the geoidal heights information is required. Common point information is required, and this is used in larger areas where the height of the problem can be solved by adapting ellipsoidal heights for the common points and performing 3D transformation. Now coming to 2D transformation, where we have only two dimensions, having only 2 points, two sets of planes represented by x and xt, where the transformation parameters are unknown. In a wider three-dimensional case, in three-dimensional case, we had used common points. Here we can use only equations. So two common points yielding two equations are sufficient to solve the unknown parameters by using the same least square method. xt is equal to c plus mu rx with a scale factor mu. Shift of c is equal to c1 c2 rotational matrix cos alpha minus sin alpha sin alpha cos alpha, having a single rotational angle, and with xt and yt as this equation c1 plus mu x cos alpha minus mu y sin alpha yt is equal to c2 plus mu x sin alpha plus mu y cos alpha with values of p is equal to mu cos alpha, q is equal to mu sin alpha. Then the linear equation will become xt is equal to c1 plus px minus qy, yt is equal to c2 plus qx plus py. So the scale factor and the rotation angle can be determined by mu is equal to square root of p square plus q square, tan alpha is equal to q by p. So what does this does? This two-dimensional transformation. So the solution can be obtained by transforming the Cartesian into ellipsoidal and iterative procedures, and for all the network points on the ellipsoidal points, mapping them into surface coordinates and appropriately mapping the formulas to the ellipsoidal of the local datum information. Then determining four parameters of two-dimensional similarity, and at last transforming them back to the plane coordinates in local system. This is what. Then this data transformation works well even without height in form, without height information. I should have combined this information, which is height information. Without height information, we can also with this do 2D works for small size networks, lower elevations, and for larger geodetical heights. The coordinates depend upon the dimension and not the displacement. So this dependency may lead to a distortion of the point clusters in which the similarity transformation is not matched. So one way to overcome this problem is that applying other transformations such as affine transformation between two coordinate sets in the plane. And there is another way also that to transform the coordinates of common points using approximate ellipsoidal heights rather than individual ellipsoidal heights. So the parameter of three-dimensional similarity transformation can be derived that enables the approximate transformation of all GPS coordinates into local data. So this transformation is being achieved by an approximate shift vector to GPS coordinates and then mapped into plane. And finally, the similarity transformation in two-dimensional space. But this is about your two-dimensional transformation, 2D and 3D. Next is DOP, dilution of precision factor. So this DOP is an important parameter in determining any positioning of static or kinematic. The geometry of the visible satellites is an important factor with high quality, especially for point and kinematic surveys. So the geometric changes with the time due to relative motion of the satellite is called as dilution of precision. The dilution of precision is defined as a factor where the geometry of the system changes with time due to relative motion of satellites. Is the sense when the satellite moves from the satellite is always in rotation along the Earth's surface. So due to this, the positioning of the satellite will vary. Latitude, longitude, and altitude also may vary. So that changes has to be determined. How much DOP is being done. So that is what that geometry is. What is DOP factor? Dilution of precision. Okay. So the solution for the unknown coordinates from the 2D and 3D, we can design a matrix, A matrix as this. A is equal to minus x1 of t minus xi naught divided by eta I of 1 in the initial positioning 0 of t minus y1 of t minus yi naught divided by eta I1 naught of t minus z1 of t minus zi of naught divided by eta 1 naught 1 of t into c. So what is this is that position of x coordinate, y coordinate, z coordinate. X, y, z coordinates. First position at 1, at 1th position. And after some time, it moves on. So at second position is the same. Instead of 1, 2. In third position and in fourth position, and it goes on. So I consider that the vectors which is being obtained by these 4 satellites, a specific position from the 4 satellites 1, 2, 3, 4. I write it as it is. Okay. So then this would be your scalar triplet form. Del I4 minus del I1, del I3 minus del I1, and del I2 minus del I1, which is scattered in this matrix. QXX, QXY, QXZ, QXT, QXY, QYY, QYZ, QYT, QXZ, QYZ, QZZ, QZT, QXT, QYT, QZT, and QTT. So this is obtained by the DOP matrix. QX is equal to AT into A the whole inverse. So AT is here, A is here, transition, transposition, transpose of that matrix and inverse of that. So the critical configuration can be given by this body to a plane. So where the DOP can be calculated from the inverse of the normal equation of the solution, as in this. So in this case, the weight matrix is assumed to be as a unique matrix, and XYZ are the side positioning of one component over the other. and the cofactor matrix is this. So from this we can find geometric precision dilution, which is GDOP, geometric dilution of precision, square root of qxxx plus qyy plus qzz plus qtt. So which is all diagonals of the matrix, diagonal matrix. Then position dilution of precision, POP, sorry, PDOP, sorry, PDOP, square root of qxx, qyy and qzz. Only with respect to position. So x, y, z. It is this. And with respect to time, you can find square root of qtt, which is this. With this, you can find the DOP. And this DOP can be expressed in the equatorial system also, where the topocentric local coordinate with its axis along the local north, local east up, till up is used in the global cofactor matrix QX. So this is to be transformed into local cofactor from the global cofactor matrix Qx to a local cofactor matrix Qx using law of covariance propagation, which is given as this: Qx is equal to R Qx RT. You'll get this equation: Qxx Qxy 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 Qyy Qyh Qxh Qyh and Qhh. Why? Because we are going to find only the vertical and horizontal. We are not bothered about the altitude. So vertical positioning and horizontal positioning. Why? Because always the altitude, when we fix the satellite in space, will remain as it is. That altitude has to be maintained by the satellite, which is being monitored by the health indicator. So GDOP, geometric accuracy in position and time; PDOP, accuracy in position; TDOP, accuracy in time; HDOP, accuracy in horizontal; PDOP, accuracy in vertical. So I'll give you 2 or 3 minutes. If you have any queries, you can ask. So with this, the outline of today's or this session, 4 topics. This word, since we had lost so many Saturdays, 2 Saturdays holidays, 2 Saturdays placement class, one Monday as your holiday. So 5 classes has gone. So I was unable to complete the unit 1 since only 3 classes were conducted for GPS, I think so. So this is the 4th class. So with this we complete unit 1. I'll give you 2 or 3 minutes of breathing time for you. Then we'll start the next topic. These were the things that we had seen. Our unit 1 comprises of history of GPS, PC4 system, Iran, NNSS, NNSS, navigation with GPS, surveying with GPS, Navstar, GLONASS, GNSS, followed by GPS constellation, space segment, control segment, user segment, and DGPS, WADGPS, static, kinematic, pseudo kinematic, 2D, 3D, and DOP. So these are your syllabus, history of GPS, which we had covered. BC4, Iran, NNSS, Navstar, GLONASS, GNSS, GPS constellation space segment, control segment, user segment, single frequency, dual frequency, L1, L1 and L2, relative, point relative, differential GPS, static and kinematic, 2D, 3D, anti-spoofing, selective availability, DOP factors. So any doubts in this? Kindly await. I'll take attendance in few minutes. Okay, I'll call you one by one. I will call you one by one. Turn on your mic and give your attendance. Nagarajesh,
Yes, sir.
Madhav Reddy,
Nine.
Madhav Reddy, Lokesh Rahul,
Yes, sir.
Prashant.
Sir, Madhav, sir.
Sir.
Sir,
Your name, please.
Madhav Reddy, sir.
Okay. Wait in the meeting. I'll give you an important instruction. Do not leave.
Sir,
Okay. Be in the meeting. I'll give an important instruction regarding internals.
okay, sir.
Prashant,
Yes, sir.
Surya Bharat,
ఏంది అంతా బ్యాక్ నుంచి వస్తాను.
Surya Bharat Kumar, Balaji,
Yes, sir.
Alita,
Yes, sir.
Vinay Kumar, Sundar Vinay Kumar, Bhargav Ram, Bhargav Ram, Sundar,
నన్ను ఇంకా పిలవలా. ఫ్రెండ్కి ఫోన్ చేస్తాను.
Sri Ramulu Sundar, Ragasudha,
Yes, sir.
Satish Kumar, Rakesh, Raghunath Reddy, Sri Devi,
Yes, sir.
Akhil, Venkat Pavan, Sivasai, Vishnu, Purnashri, Babu,
Yes, sir.
Arvind,
sir.
Guru Prasad, Ajay,
Yes, sir. Present, sir.
Abhiram Sharma, Ashok Naidu, Malata,
Present, sir.
Shivaram Ganesh,
Present, sir.
Nikhil Chaudhary, Nikhil Chaudhary, Sai Jyoti,
Present, sir.
what Sai Jyoti today's work over?
Over, sir.
Very good. Kirti,
Present, sir.
Harish Chaudhary, Harish Chaudhary, Harish Chaudhary, Partha Sarthi,
Present,
Patar,
sir. Sir,
last week absent last time.
మాకు సిగ్నల్ రావట్లేదు సార్ ఊర్లో.
Rainy season,
ఫుల్ రెయిన్స్ సార్, ఫ్లడ్స్. కాల్ బయట పెడతానికి కూడా లేదు సార్.
in which place flood it is?
ఒంగోలు సార్, ఒంగోలు ప్రకాశం డిస్టిక్.
You are in?
అక్కడే ఉన్నా సార్, ఒంగోలు ఓన్లీ.
Okay. Jayant,
Present, sir.
ఆబ్సెంట్ సార్.
Present, sir.
then who is giving attendance for Jayant?
Uh,
If he is absent. So anybody name is left out or anybody who has not been marked can unmute their mic and give attendance. I will wait another
Raghunath
5
Reddy,
minutes for attendance. I'll give you 5 minutes more for attendance if anybody is. Anybody else? Yes, name?
Puttur Raghunath Reddy.
A bit louder, please. Your name?
Puttur Raghunath Reddy, sir. C189.
Raghunath Reddy. Yeah.
Yes, sir.
Okay. Then I'll wait for another 5 minutes. If somebody can come and give attendance, I'll wait and I'll mark it. Then I'll move on to the instructions for first internal, where 21st we'll be having a test on global positioning system. Same 2 to 3:30. I'll give you those information and instruction syllabus, how to write exam, how to conduct and all. I think most probably all the 34 students for the global positioning has joined Google Classroom. So it would be appropriate for me to share and use Google Classroom effectively for conducting of test. Wait for another 2 or 3 minutes for attendance. Let me check any new. Oh, it's still in presenting. Stop presenting. Yes, Jayant, what do you want to say?
Nothing, sir.
Yes, Madhav, ready?
Session, I'll tell you one thing.
Uh, I think Raghunath Reddy's voice is not audible. You can text in chat box.
ఎవరు నెట్టుకుంటారు ఫోన్ అన్నిటికీ లాక్ పెట్టండి
Put in chat box Raghunath Reddy.
ఇప్పుడు పిల్లలు ఉంటారు మోస్ట్ ఇట్లా అంటారు మాత్రం ఫోన్ కాల్ చేయాలంటే ఎందుకు బాధలు సిగ్గు మా ఇన్ని కాలు పెట్టాను లాక్లా దీన్ని లేదు కాబట్టి అట్లా అయింది.
అప్పుడు కూడా పెట్టాను కదా పెట్టాను
ఆప్షన్ ఉంది మచ్చా ఆమె
యాప్ లాక్ సపరేట్ ఎక్కించుకున్నావా లేకపోతే
Yeah, Ajay, third year exam results means which semester you are asking? Sixth semester or fifth
Sir,
semester?
both. Sixth one, sir. Sixth semester, sir.
Sixth semester. All the process for that is being done and it is going on.
Okay, sir.
The controller of
I have to
examination
submit the
is
mark list, sir.
the controller of examination is working on the same results for your batch and your juniors batch also, and the sub junior batch. So for all of them, they are working. For the time being, they are dispersing certificates for fourth year. Those who have been passed out, your seniors. Those who have completed their examinations, got results. They're more concentrating on that, and the work for yours result. They are working on that. We may expect another maximum 10 to 15 days maximum. Within that, you may receive your results, and the information of that will be posted in university website. Have a regular check on the university website, and as soon as I receive it, I will pass it on to the WhatsApp group that we are having. Okay, Ajay. Okay, then attendance. So I'll close the attendance. I'll read out the absentees once again. Harish Chaudhary, Nikhil Chaudhary, Ashok Naidu, Abhiram Sharma, Guru Prasad, Purnashri, Vishnuvardhan, Sivasai, Venkat Pavan, Akhil, Rakesh, Satish Kumar, Sundar, Bhargav Ram, Bharat Kumar. Yeah, these are the absentees for today's session. And information related to first internals is that I am very much more concerned about global positioning system. Since today only we had completed the syllabus, only today we had completed the syllabus of Unit 1. So I would like to keep only Unit 1 as your syllabus for first internal test. So how do we access or what is the pattern for examination is that for global positioning system, global positioning system will be having five five part B questions. So each carries 10 marks. Totally 50 marks. All the 5 questions from Unit 1 will be posted in Google Classroom exactly by the time of examination. And everyone should join the meeting on the particular day of examination. Should confirm that you have received the question paper by providing the appropriate details in the meeting, and you should start writing in A4 size sheet paper. Scripting has to be done, and after scripting you need to scan the answer sheet, send it in Google Classroom,
Google Classroom.
and then turn in Google Classroom. I think last semester most of you would have done this. So again, I give instruction for this is only for global positioning system. So this is how is the method we are going to adopt for conducting first internal test. First internal test for global positioning system. Any questions you can put in chat box. Any doubts or any questions? And regarding the material for Unit 1, for Unit 1, I'll share the materials in Google Classroom and check for materials. You can see the Unit 1 materials will be uploaded by today in Google Classroom only. No sharing in WhatsApp and no emailing separately. everyone has to access your Google Classroom. If you are a mobile user, you can download the Google Classroom app. It is available in the Play Store. So make use of the Google Classroom effectively. So any queries you can put in chat box. Thank you.